everyone, welcome to Mr. Naik Math. By the end of this video, you will learn how to find dy dx in implicitly defined functions. We will also explore graphs of implicit equations and what dy over dx means graphically. Let's first see the difference between an explicit and an implicit function. An explicit function is when you have f of x or y on one side of the equation, and on the other side you have an expression which only contains x. Now it doesn't need to be restricted to x and y. For example, you could have a function f of z, which is z squared sine z minus e to the z cosine 6z in this case. But the important thing is that your right hand side is only in terms of the independent variable, which is z. So in general, dy dx is going to look like f prime of x. So even your derivative is going to be some function of x. This is called the derivative function. Now in the case of implicit functions or implicitly defined functions, implicit equations, you don't have y on one side and on the other side you have x. In fact, sometimes it may not even be possible to isolate for y on one side and move all the x terms to the other side. So for example, in this case, it may be possible. You can say y equals, let's say, plus or minus square root of 1 minus x squared. But you can probably tell that in the next example, it's going to get even harder to isolate for y. This is a cubic equation in y, and it's practically impossible to say y equals some function of x. Whereas in the next function, in the next example, it is literally impossible to go y equals something, some expression in x. So implicitly defined equations or functions have both a mix of x and y in the equation. In this last example, it may look like an explicit function, but it's not explicit because the right hand side has both x and y. In the case of implicit equations, dy dx, which is the rate of change of y with respect to x, is going to be some function in both x and y. Compare that to dy dx for explicit functions, which is a function of x, whereas here it's going to be a function of x and y. Now there's no new theory when it comes to differentiating implicit functions. All you need to know is the chain rule, and I've written the chain rule here for reference. What this means is it's the derivative of f with respect to g multiplied by the derivative of g with respect to x. Now let's say that g of x is y. What does the chain rule become in this case? We get d dx of f of y, where y is some function of x. That is going to be equal to f prime of y, that is the derivative of f with respect to y, multiplied by g prime of x. But in this case, g prime of x, notice, is just dy over dx. And therefore, the derivative of f of y can be written as f prime of y multiplied by dy over dx. And we're going to use this form to differentiate implicit equations. Let's consider the example d dx of y squared. Now in this case, y is assumed to be some function of x, and so we can apply the chain rule. So using the formula that we derived earlier, we can say the derivative of y squared is going to be 2y multiplied by the derivative of y with respect to x, which is dy over dx. We can do the same thing over here, but this time we have both a mix of x as well as y. Now the derivative of x with respect to x is just 1, and the derivative of y squared with respect to x, we derive that over here. That is 2y dy dx. So notice how we are actually taking the derivative with respect to x of an expression that contains both x as well as y. This is going to be very useful in implicit differentiation. In the next example, we have the product rule. Because we have two different functions, you can treat this as one function, this is another function. So d dx of x times y squared, this is going to be the derivative of x, which is 1 times y squared, plus x times the derivative of y squared, which is 2y dy dx. We can simplify this and just call it y squared plus 2xy dy dx. We are now ready to do a problem which contains implicit differentiation. So consider the circle x squared plus y squared equals 4. We have to find dy dx for this circle and therefore find the slope of the tangent line for the circle at 1, negative root 3. If you want, you can verify that this point actually lies on the circle. So to find dy dx, we need to differentiate both sides of this equation with respect to x. So the derivative of x squared plus y squared with respect to x, that's going to be 2x plus the derivative of y squared, remember, was 2y dy dx equals, and now the derivative of 4 with respect to x is just 0. And now our goal is to find dy dx. So rearranging for dy dx, I can subtract both sides by 2x. So subtracting 2x on both sides, we have 2y dy dx equals negative 2x. And dividing both sides by 2y, we have dy dx equals negative x over y. Let's not forget what the dy dx represents graphically. Graphically, it is the slope of the tangent line. So for example, we want to find the slope of the tangent line at 1, negative root 3. That means this is the x coordinate, this is the y coordinate. All we need to do is plug in these x and y values into our expression for dy dx. So we can say the slope of the tangent line at 1, negative root 3 is going to equal negative 1 over negative root 3, which is going to be 1 over root 3. I have plotted the circle and the tangent line so you can visualize what's really going on. Now approximately 1 over square root 3 is like 0.58. And what this means is if I were to draw a tangent line at this point, this is 1 negative root 3, the slope of this tangent line should be around 0.58. So if I were to, make a sort of a triangle over here and measure the slope, the rise over run, that's going to be 0.58. In our next example, let's find dy dx for this equation. Now this equation looks a bit complicated, but our procedure should not change. We have to differentiate both left and right side with respect to x. So differentiating x cubed with respect to x, we have 3x squared plus the derivative of y cubed is going to be 3y squared multiplied by the chain rule by dy dx. Differentiating the right side, we need to use the product rule. So this is going to be 2 multiplied by the derivative of x, which is 1 times y, plus x times the derivative of y, and the derivative of y is just 1 multiplied by dy dx. Now our goal is to find dy dx, but there are 2 dy dx's in this equation. Well, that just means that we have to treat this one and this one as 2 like terms and somehow combine them to find dy dx. Let's see how we can algebraically manipulate this. So we have 3x squared plus 3y squared dy dx is going to equal, expanding the 2, we have 2y plus 2x dy dx. Now what we need to do is to bring all the dy dx terms to one side and everything else to the other side. So for example, I'll bring all the dy dx terms to the left side and the other stuff on the right side. So we have 3y squared dy dx minus 2x dy dx equals 2y minus 3x squared. I just moved this one to this side and moved this one to this side. There's nothing deep going on here. So the next step is to factor out the dy dx. We have 2 terms containing dy dx. They both have dy dx in common. Let's pull it out of the expression. Dy dx 3y squared minus 2x equals 2y minus 3x squared. And now finally we can isolate for dy dx by dividing both sides by 3y squared minus 2x. So finally dy dx equals 2y minus 3x squared divided by 3y squared minus 2x. Now the first part of the question, that is finding dy dx, is done. This is all we need to do for dy dx. But they've also asked us to find the equation of the tangent line. Now let's not forget that dy dx is nothing but the slope of the tangent line. To find the equation of the tangent line, I'm going to use the point slope form, y minus y1 equals m times x minus x1, where m is the slope of the tangent line and x1 and y1 are the coordinates of the point. So in this case x1 and y1 are both going to be 1. But first let's find the slope of the tangent line at 1, 1. We have dy dx at 1, 1 is going to equal negative 1. So that's our dy dx. But we're not done yet. We have to find the equation of the tangent line. This is the slope of the tangent line. But we have to find the equation of the tangent line. So plugging in this m value into this point slope form, we are going to get the equation of the tangent line as y minus 1 equals negative 1 times x minus 1. We can even convert this to slope-intercept form if you like. This could be y equals negative x plus 2. Now I have graphed this equation for you. We have our original graph in red, which looks like this amazing loopy looking graph, x cubed plus y cubed equals 2xy. And we have our equation of the tangent line, which is y equals negative x plus 2. Notice that the slope of this tangent line, if I were to take the rise over run over here, this is going to be 3 and 3, and it's a negative slope, so it has to be negative 1, which is what we found earlier in the first place. Our slope is negative 1. For our next example, let's find dy dx for y equals cosine of x plus y. Now this looks like an explicit function, but it's not explicit because there is y on the left hand side as well as the right hand side, and well, practically it's impossible to isolate for y on one side and have only x's on the other side. So we are going to proceed as before, differentiating both sides with respect to x. So the derivative of y with respect to x is just dy over dx. And the derivative of cosine of x plus y. So for this, we have to use the chain rule. The derivative of cosine of anything is negative sine of anything, and that anything is x plus y in this case. But by the chain rule, we also have to multiply this expression by the derivative of what's inside here, and that is 1 plus the derivative of y is dy dx. Expanding and collecting like terms, let's see what we get. Dy dx equals negative sine x plus y. Negative sine x plus y times 1 is just negative sine x plus y. And negative sine x plus y times dy dx is going to be minus dy dx times sine x plus y. Now again, let's not forget our goal is to find dy dx, but there are two dy dx's over here. So let's move this entire term, which contains dy dx, over to this side. We have dy dx plus dy dx times sine x plus y equals, what remains on this side is simply negative sine x plus y. Factoring out a dy dx from both these terms, we get dy dx 1 plus sine x plus y equals negative sine x plus y. And finally, dividing both sides by 1 plus sine x plus y, we have dy dx. I have added the graph here for your reference. Now if you notice, there might be some points where the tangent line would actually be a vertical line. So if, for example, over here, if I were to draw a tangent line, it would be vertical. And over here, since it's a cosine function, it is actually periodic. And so there are multiple points where the tangent line would be vertical. Now this happens because we have a 1 plus sine x plus y term in our denominator, and if our denominator is ever 0, then our derivative is not defined. And if the derivative is not defined, then we know that the tangent line could be vertical. If you're interested, you could analyze this function yourself and try to figure out the exact points where the derivative is not defined. To summarize implicit differentiation, we first differentiate the entire equation with respect to x. Whenever there are terms containing y, we use the chain rule. For example, the derivative of y squared is 2y dy dx. If a term only contains x, then we don't need to attach a dy dx to it. The next step is to collect all the terms containing dy dx on one side of the equation and then move all the other terms to the other side. Finally, we factor out a dy dx and isolate. This dy dx will usually be a function containing both x as well as y. Now that's it for this video. I will be covering in a future video more applications of implicit differentiation, specifically finding the second derivative using implicit differentiation. Thank you for watching and see you in the next video.